Good afternoon, students. Lecture 2 is about linear dynamical physical systems. We shall begin our discussion by describing a defining property of the linear system known as linearity, which can be further split into the property of homogeneity and superposition. That will be followed by some examples. A closely related concept of time invariance will also be discussed. And in combination with the linearity property, we shall develop the differential equation representation of the linear systems. An equivalent representation in the form of the transfer function will also be described. And in the end, we shall describe some typical inputs occurring in real-life linear dynamical systems. We shall conclude our lecture by describing the canonical form of some basic linear dynamical systems, including the first order system as well as the second order system with the corresponding real life examples. So the question is, why should one study linear dynamical system? And the reason being that many real life systems can be reliably modeled as linear systems. Some of these examples include the servo mechanism in the hard disk drive. Now, in this mechanism, we have an actuator known as the VCM actuator, which is housing the read and the write sensors, which are responsible for writing data on your disk player of the hard disk drive system. The car suspension system is also a good example in which we are interested in engineering the suspension system which is robust to external disturbances. And then we also have an example of robotic manipulators which are deployed for range of tasks in the industrial settings. Another reason is that linear systems are easy to model and simulate, and that is because we have wide range of tools to predict their output for various inputs. And some of these tools are based upon the time domain techniques such as convolution, and other techniques are based upon the information of the response when taken in the frequency domain. A well-known tool in this regard is Fourier transform. Let us start with an example of a simple series RC circuit. It contains a resistance R connected in series with a capacitor C. The input to the circuit is a voltage source Vin, and the output is taken as the voltage across the capacitor, that is Vc. There's also a switch in the circuit which closes at time t equals to 0. That's when the analysis begins, and the switch remains closed afterwards. Now let us analyze the output that is available when we have a specific kind of an input. So the input in this case is known as the step input, and it will be discussed in detail later on in the lecture. This is a step input which instantaneously jumps from 0 volt to V volt and then remains steady at V volts afterwards. Then, from your knowledge of electric circuit transient analysis component, you can immediately see that the output voltage, that is the voltage across the capacitor, will not jump instantaneously, and that's because the capacitor resists an instantaneous change in the voltage. Instead, the voltage is going to build up gradually, and eventually it will approach the value that equals V, the input voltage. And how long do we need to wait till the voltage rises to the value V depends upon the value of resistance and capacitance when put together in the form of time constant. Now for the same circuit, if the input voltage V in is adjusted to the step input, which remains steady at 2 volts, then it is easy to generalize and to say that the output voltage, the voltage across the capacitor, will also try to approach value 2V steadily as before. Therefore, we can generalize it for any constant K, and we can say that whenever the input voltage is scaled by a constant factor K, that is the V in becomes K times V, then this gives us the corresponding output, which is also scaled by the same scaling factor K. And this brings us to the first property of the linear system, known as the property of homogeneity. This property says that if the input V in gives you an output Vc, then scaling the input by some constant factor K gives you the output, which is also scaled by the same constant factor K. So after discussing the property of homogeneity, let us move on to the next important property of the linear dynamical system, and that is the property of superposition. To understand this property, let us consider the same RC circuit, and this time the input is not a step input which remains steady at V volt, rather the input drops to 0 after certain time t0. The input in this case represent a pulse of a short duration. For this input, I have drawn the output, which is the voltage across the capacitor, obviously, and the nature is something similar to what we saw before, except that once the capacitor voltage has reached a value V, then it decays after time t0, and that's because the input becomes 0 after t0. And as before, the output steadily rises until it reaches value V and remains steady until t0, and afterwards it decays and approaches 0. The question is, how did we get this output? To understand this, the first thing we need to know is that the input, which is a short duration pulse, can be written as the sum of two different input signals, V in 1 and V in 2. So V in 1 instantaneously jumps to value V at time t is equal to 0, but V in 2, the second input, uh, attains minus V after time t0 and then remains steady at that value. And therefore, if you look at V in 2, it appears that it is kind of a time shifted version of V in 1. Nevertheless, when you add V in 1 to V in 2, you get an input representing a pulse of short duration. The corresponding schematics are shown on the right. So the principle of superposition has been used, that in this case we have superimposed the two inputs to construct a new input, which you may call as V in 3. Now for each of these inputs starting with V in 1, we know we can get, we know exactly what is the output. So for V in 1, the output is VC1, and we've seen this one before. The output VC1 gradually rises to the value V. And for V in 2, we have the corresponding output VC2, and it also follows the input, which in this case is minus V. So note that the output will be inverted because the input is also inverted. So the output will try to approach value minus V, and it will start its slide towards minus V at time t naught. Therefore, if the input V in 1 is being added to input V in 2 to get a new input, which is the sum of the two, then the principle of superposition says that the corresponding outputs should also be added up. And therefore, when you add VC1 with VC2, this is the output that we are going to get. So principle of superposition has simplified our analysis of the output when the input is a slightly more sophisticated signal. To complete the definition of the linear system, we include the property of superposition, and together with the homogeneity property, we have defined the linear system. So a linear system is one which exhibits the properties, two properties, both the homogeneity as well as the superposition. So the property of superposition that we saw has been summarized over here. The question is, how do you combine these two properties into single condition? So when you combine the two properties that define linearity, the condition becomes that if you have two inputs, V in 1 and V in 2, and the corresponding outputs are VC1, VC2, and we make use of two constants, K1 and K2. The condition says that if you have a weighted sum of the two inputs, where the weights are defined by the corresponding scaling factor, K1 for V in 1 and K2 for V in 2. Then this should give you a corresponding weighted sum of the output such that K1 multiplied by the VC1 is added to K2 times VC2. So when you add the corresponding inputs scaled by corresponding scaling factors, what you should expect, and in other words, if a system is linear, then the weighted sum of the inputs should give you the weighted sum of the outputs, where the weights should be the same in both the cases, at both the inputs and the outputs. In general, in dynamical systems, the inputs and the outputs are variable. In some sense, we represent them as a function of time. So therefore, if we talk about notation, we can also represent the above condition by assuming that in a more generalized form, x1 of t and x2 of t are the two time-dependent inputs. Then the corresponding output would be, say, y1 of t and y2 of t, and we can rewrite the above condition in the form of the weighted sum of the inputs x1 and x2, giving us an output in the form of the weighted sum of the outputs of y1 and y2. Let us show how can one formally prove that the given series RC circuit is linear. So for that, we need an input-output relationship, which in this game is described by a first-order differential equation. How to drive this differential equation will be discussed later on, but assuming that this differential equation is given and it describes a relationship between the input V in and the output VC, and obviously there are some coefficients described by the value of resistance and capacitance. And we can say that the product of resistance and capacitor defines the time constant tau so that the two can be lumped into single parameter. The proof will proceed by saying that let's say there is an input V in 1 to the system, and that will give us an output VC1. If this is the case, then it is clear that if we plug V in 1 as the input to the differential equation, then the output should be replaced by VC1. In other words, when we say that the input VE1 gives you an output VC1, it means that the input-output relationship remains satisfied when the input is replaced by V in 1 and the output variables are replaced by VC1. And you should note that the output variable is appearing once without derivative over here and once with derivative here. That is when it is multiplied by the coefficient tau. Then we say that there is another input to the system V in 2 which gives us an output VC2. And if this is the case, then the differential equation should satisfy differential equation will remain satisfied if the input is replaced by V in 2 and the output variables are replaced by VC2. So now we have two equations, 1 and 2. And then if we define a third input, let's say V in 3, which is the weighted sum of the two inputs, k times V in 1 plus k2 times V in 2. Then this input, suppose, give us an output VC3. Then the differential equation will be satisfied by replacing input with V in 3 and the output with VC3. That defines our equation number 3. So in order to show that this circuit is representing a linear system, then by definition we need to show that VC3 equals the weighted sum of the corresponding outputs, that is VC1 and VC2. These are the outputs which correspond to the inputs V in 1 and V in 2 by definition. Now, in order to see that V in 3 does satisfy the property that we have just described, that is VC3 should be written as the weighted sum of the outputs corresponding to the inputs VC1 and VC2, what we can do is that we make use of equation 1 and equation 2, which contain expression of the input, the first two inputs V in 1, V in 2, and the corresponding outputs VC1 and VC2. We're going to multiply the first equation with K1 and the second with K2 and then add them up. And this will give us an expression in the form of equation number 4. The left-hand side of equation 4, it can be seen that it is simply tau times the derivative of VC3 plus VC3 without derivative. And that comes from equation number 3 from the last slide. The left-hand side is the same as equation number 3, and this has been done on purpose. So this addition of equation 1 and equation 2 after scaling with corresponding numbers has been done so that the left-hand side becomes equal to equation number 3, and that's where we find the output VC3. Now we can easily say that the equation 3 and equation 4, they can be compared for the coefficients of the coefficient tau. And so if you compare equation 3 and equation 4, in a sense that you compare the coefficient of tau in both the equations. So this means that the derivative of VC3 equals K1 derivative of VC1 and K2 times derivative of VC2. And likewise, VC3 equals K1 VC1 and plus K2 times VC2. So in both cases, we have a unique solution, which is just VC3 equals K times VC1 plus K1 times VC1 plus K2 times VC2. And that's all that we were looking for. The VC3 is actually equal to the weighted sum of the corresponding output with the same weights K1 and K2. Therefore, we can say, and we have proved that the RC series circuit is representing a linear system. Now let's take an example of a nonlinear system. And here we have a diode, the same input Vin and the output Vc taken as the voltage across the capacitor. Now we claim that this circuit is an example of a nonlinear system, but how we are going to show this? There are several ways to show that this system is nonlinear, but the simplest one would be the one that just utilizes a counterexample, which is that suppose if V in 1 is 10 times the voltage drop across the diode, then the output voltage Vc will follow the input voltage, which is 10 times Vd minus the voltage drop across the capacitor. Voltage drop across the diode. So this is true as long as the Vin is non-negative. But what if Vin represents a negative quantity such as minus 10 times Vd? Then we know that the diode cannot conduct in the negative cycle. Therefore, the voltage will never be able to appear across the capacitor. The voltage remains zero. And therefore, because the voltage across the capacitor is zero, this is not satisfying the homogeneity property, because had this system been linear, the voltage across the capacitor would simply had been the minus of the voltage when the input was positive, that is 10 times Vd. So just because we have flipped the sign of the input, the output sign is not negative, rather it is zero. And this defies the homogeneity property, because in homogeneity property, if the input sign is reversed, the output sign is also reversed, but the magnitude remains the same. Therefore, because the property of homogeneity, and by the way, there is a typo here, so this really should be G-E-N-E-I-T-Y. This property has been violated, therefore it's an example of a nonlinear system. Note that several electronic circuits which contains semiconductor components such as diodes, BJTs, and MOSFETs, they are usually nonlinear systems. By contrast, electrical circuits, which are defined by three components, resistance, capacitance, and inductance, they exhibit linear behavior. Before proceeding, it is important to note that even if the system that we are trying to model is nonlinear, in reality, it is still possible to approximate its behavior using some equivalent linear system for some restricted but applicable range of inputs. So in other words, we are saying that there is an approximation of nonlinearity using linearity. But the cost that we have to bear lies in the range of applicable inputs. So a typical example might be an electronic amplifier. So we know that amplifier makes use of the transistors, and amplifier amplifies the input signal, input voltage for example, over certain range, over certain bounded values, beyond which the amplifier output begin to chop off the input voltage. It begins to distort the input voltage. Very often that falls into the small signal analysis. Another example is a DC motor, which may suffer from saturation in reality. That is, we cannot expect the torque to be always perfectly proportional to the current, because uh, although the current passing through the coils of the motor produce magnetic field whose magnitude is proportional to the current, but that linear behavior no longer remains valid once the current exceeds certain value. And same goes for range of pneumatic and hydraulic actuators. However, once the system is modeled as a linear system, it is easy to simulate for its response to different parameters. For example, we can talk about motor mass moment of inertia, in case of amplifier, the amplifier output resistance and fluid inductance. And because of the fact that we have a model available for simulation, we can tweak the values of these parameters and optimize the performance of our linear system. We saw that a system described by the first order differential equation was linear. The system, which was actually an RC series circuit, had this form. It was a first order differential equation where A1 was the time constant and the remaining coefficients were just unity. In general, it can be shown that an nth order differential equation of the form shown here also represent a linear system. In this case, the order of the differential equation is determined by the coefficient which are appearing on the left hand side with the output variable y of t. So the coefficients a0, a1, an minus 1, an. And the order is not dictated by the coefficients which are appearing on the right hand side containing the derivatives of the input. We shall discuss in detail how do we determine the order of the system, but here we are restricting our definition of the order to the order of the differential equation. So as part of your homework exercise, you are required to show that the following system is linear. However, this system, by contrast, is nonlinear, and you notice that this differential equation contains a constant value which is being added to the input. That's what makes it nonlinear. So I expect students to be able to formally prove this nonlinearity in their homework exercise. Besides linearity, we seek another important property in dynamical system, that is the property of time invariance. So loosely speaking, we say that the system is time invariant if its input-output relationship remains intact and doesn't change with time. So mathematically, if we say that if the input xt gives you an output y of t, then if the input has been delayed by time t naught, then the output is also delayed by time t naught. So in case of the RC circuit example, we saw that by delaying the input by some time t naught, the output was also time delayed. However, one should note that there was an assumption of zero initial conditions. So that assumption needs to be taken into account here as well. A system which is both linear and time invariant is known as the LTI system, linear time invariant system. Linear time invariant systems are particularly interesting because of the feasibility of the calculation of their output, as we shall discuss in the next slide. It is relatively easy to calculate the output, that now we call that output as a response. Both terms are synonymously used here. We can calculate the response of an LTI system easily, and there is a mechanism for that known as the convolution. So you're familiar with the convolution. That is, I expect students to be able to convolve, to be able to at least understand how do we convolve the two signals or the two functions. And in case of the linear time invariant system, we say that the output y of t equals input x of t that is convolved with h of t, where h of t is known as the impulse response of the system. All right, so we first need to understand what do we mean by the impulse response. So first we need to define the impulse. What do we mean by impulse? In particular, we are going to give you the definition of a unit impulse. A unit impulse is a signal which has zero width and infinite height, that so that the area under this function, or if you integrate this function, the area under this strange looking curve remains equal to 1. And the representation is slightly unconventional because this 1 is not representing the amplitude, it is representing the area under the impulse curve. In some sense, this impulse is defined in the limit of a short pulse, as we saw before. So suppose we have a short pulse of duration delta t and whose height is 1 over delta t. In the limit, when delta t approaches 0, we can see that the width of this pulse approaches 0 and the height approaches infinity. This is one way to define the impulse or to approximate the unit impulse. However, there are other ways, for example, using triangular pulse as well, but that's beyond the scope of our current discussion. So the impulse response of the system is the output of the system when the input is unit impulse, represented by delta t or the delta function. So if we know the output of the system when the input is unit impulse, then we can calculate the output of the system for any input x of t using this convolution. So this is an interesting attribute of an LTI system, that we can readily calculate the output by convolving the two signals. So as we said, that convolution is going to give us the output or the response of the system. This is a time domain attribute or the time domain technique. Now, there is an alternative description that is obtained when we take the Laplace of the convolution. So if we take Laplace of both sides of this equation, y of t is h of t convolved with x of t, then we know that the convolution turns into multiplication in the Laplace domain. Therefore, if y of s denote the Laplace transformation of y of t, h of s represents the Laplace transformation of the impulse response, and x of s represents the Laplace of the input x of t. Then h of s is simply y of s divided by x of s. This gives us the transfer function representation of an LTI system. And in this course, we shall often refer to the transfer function representation. We shall often go back and forth between differential equation and transfer function representation based upon the application at hand. So when we talk about going back and forth between the two representation, we are essentially talking about interconvertibility of the two representation. That is the representation based upon differential equation and that based upon the transfer function. And if we generalize the idea of the Laplace of the derivative of some function, then we know that suppose the Laplace of some function f of t is capital F of s, then the derivative, Laplace of the derivative of f of t will be s times f of s, and the nth derivative would be simply giving us s to the power n multiplied by f of s in the Laplace domain. So if we do a simple example here, try to convert the following nth order differential equation into the transfer function, then all we need to do is to take a Laplace on both sides. When we do that, we get a polynomial in S on the left hand side. This is the nth degree polynomial, and we have a polynomial in S of degree m on the right hand side, that is the input side. And after rearranging in these polynomials in the transfer function representation, we have an m degree polynomial in the numerator and the nth degree polynomial in the denominator, with the corresponding weights an minus 1 to a naught in the denominator and b's in the numerator. A representation similar to the transfer function form can also be used such that the Laplace variable s is now replaced with the operator capital D, where D operator is defined as the derivative operator, and D raised to the power k, or D with exponent k, represent the kth order derivative. So this gives us the transfer function form, not in the form of Laplace variables capital Y or X. Rather, we can go back to the time domain representation, small y, small x, or small y divided by x. Obviously, these are function of time, so you can put a t here easily. And we are back in the time domain because we are making use of these derivative operator, which is performing differentiation d over dt. So here again we have a polynomial, nth degree polynomial in the denominator and the nth degree polynomial in the numerator, and the same, it looks very similar to the transfer function, and all we have done here is that we have replaced s with the operator d. So d is the derivative operator in this case. So a nice thing about this new representation is that it is possible to cluster the derivative operators and to treat them just like the variables. So in a form that we derived in the last slide, that is obtained when you relate y of t with x of t, essentially y of t divided by x of t, then we can bring all of these here, all of these d operator in the form of a polynomial on the left hand side, and the mth degree polynomial in d on the right hand side. We can bring them all together inside the bracket and have them multiplied with x of t. When we do that, we find that this d operator, once the brackets, the parentheses are open, these d operators are being applied. Each one of these d operator, the first one is dn. So this is representing the nth order derivative of y. The next one is dn minus 1, which is the n minus 1 derivative, and so on. Once we open these brackets and simplify, we get the same differential equation form from where we started. So all of these transformations, or all of these representations, are essentially equivalent, and because they all correspond to the same differential equation, thus the same system. Now let us look at some of the typical inputs that occur in real life linear dynamical systems. On the left hand side, we have an ideal input, and these are compared with the real or realistic inputs. Already we saw an example of an input known as the impulse. Now impulse is more like an ideal input signal. In reality, however, we deal with the pulse. And we saw earlier that this impulse can be approximated by a pulse in a limit when the width goes to 0 and the height goes to infinity. A very commonly used input that we will often be dealing with in this course is the step input. That is, when the input suddenly jumps from 0 to some steady value. In reality, however, the input can never jump instantaneously from 0 to some steady value. Rather, it will take some time. So a more realistic input might be the ramped step. The third input is the ramp, which is a monotonically increasing input with a constant slope. Now, in reality, we don't have an input which is constantly increasing, because that itself representing an unbounded signal, or a signal which has infinite energy. But therefore, we often utilize the sawtooth, or something similar to a triangular waveform, the signal that is linear over a certain range of time and then drops to 0 and then start over, and then it reaches that value and then drops back to 0. And finally, we have a very familiar input known as the sinusoidal input. So what I have drawn here is the sinusoidal input of the frequency f, and this input is quite often used to analyze the system output or the response to a particular frequency or a range of frequency. And as we pointed out earlier, that we have some tools to analyze the output of the system, and some of these tools work in the frequency domain. So in frequency domain, we often talk about the output of the system when the inputs are sinusoids or the sinusoidal input. And we're often interested in knowing the output of the system for a wide range of frequency. And from there, we can determine the frequency response and some associated properties such as the bandwidth of the system. And again, the discussion of the bandwidth of the system will be done at some point later in this course. But rest assured that the bandwidth of the system in the context of mechatronics engineering is somewhat different from the bandwidth of the internet that we are all familiar with.